So this afternoon we have a talk by Rémi Coulon. He will talk about equations of Burnside groups.
Well, thank you very much for the invitation. It's a great pleasure to be back in Bonn. And so today I'm going to speak about some work I did during the program 7 years ago with Sela about equation in Burnside groups. But first I'd like to motivate this work by giving you some applications which are related to the dense automorphism problems. So these problems in general, you are given two groups, say by representation. Each one is given by representation, and you ask yourself, is there an algorithm that can decide whether the two groups are isomorphic or not? So in general, this problem is known to be unsolvable, but then you can restrict yourself to a particular class of groups. For instance, if you take only abelian groups, this is rather straightforward, that you can find a solution. There are more complicated class of groups, like if you take all habitable groups, the isomorphism problem is known to be solvable. That's a result of Sela and Adian groups. And then you can choose your own favorite class of groups and ask yourself, among these groups, is the isomorphism problem solvable or not? And for this talk, my favorite class of groups will be of pick and guess, all Burnside groups. So more precisely, let me give a definition. I would say that a group gamma is n-periodic if every element in my group raised to the n is the identity. So not only I'm asking that this group is a torsion group, but I'm asking that there is a bound on the order of the elements. And so, well, those group appears first because of the quotient of Burnside at the beginning of the 20th century, who asked that if you have a finite iterative group, which is also n-periodic, this question was, does it imply that the group has to be finite? Of course, finite groups are finite iterative and n-periodic for the right n. And so the answer in general to this question is no, that's a term due to Novikov and Adian. So there are plenty of infinite bounded torsion groups, which are finite iterative. And actually, this class is so wild that the isomorphism problem just within this class is not solvable as well. Okay, so you may wonder, well, how do we produce such group? How can we put our hands on such infinite periodic groups? So there is a very general construction which goes as follows. So I will use the following notation. So if gamma is a group, I will let gamma n be the group generating by the nth power of all its elements, so that the quotient gamma of gamma n is always n-periodic. And the main question is then, for which group gamma this quotient is infinite? And well, the theorem is as follows. If gamma is the torsion-free non-elementary hyperbolic group, then there exists some large number n, such that for every odd exponent larger than this big N, the quotient gamma mod gamma n is in this infinite. So actually, so this statement, if gamma is a free group, it goes back to the work of Novikov and Adian. That's how they prove that there is an infinite bounded portion group. You also have the proof this time for hyperbolic group by quotient. There is an alternative proof by Sela and Burnside. And if you're looking for the best possible exponent for free Burnside group, then the best value was obtained by Atkarskaya. Reached and bent. And remember what, at 550 something?
5, yeah, or 6, no, something.
Something like that. So that's the best known exponent for the case where gamma is a free. But in my talk, I will not be looking for the best exponent. I would rather have a more asymptotic approach and try to understand stuff for very large exponents. And don't ask me what those large exponents are. I don't know exactly how to compute this. Okay, so that gives you plenty of example of infinite torsion groups. And as I said previously, if you think of in the class of all groups, the work problem, the isomorphism problem is solvable among all hyperbolic groups. So you may ask sort of an analog. If you look at all the periodic quotients of hyperbolic groups, can you solve the isomorphism problem between all of them? And actually, I will ask a more specific question. So starting with a very naive remark, that if you take gamma 1 and gamma 2, which are two hyperbolic groups, well, if the two original groups are isomorphic, of course, their periodic quotients are also isomorphic, whatever the value of n is. So now the naive question is when the converse holds true. So first, I'd like to give you two obstructions that prevent this question to be, this answer to be yes all the time. And then I'll try to explain to you that besides these two rather natural obstructions, actually everything works well and can go in the other direction. So what are those obstructions? Well, let's call that obstruction A. The first one goes as follows. So I'll give you an example. That's the best way to do that. I'll take for gamma 1, the free group which is generated by two elements, say A and B. And then gamma 2 will be a group with a presentation as follows. You take A and B to be your generator, and you add a round relation, which is certain very complicated words, say, with letters A to the N and B to the N. So by some small constellation theory, you can always make this one to be hyperbolic. And well, you can see that here, the periodic quotient with exponent n of those two groups, are the same, because if you kill the nth power of every element, this relation just vanishes. But the original group are not isomorphic. One is free and the other can be made, for instance, freely indecomposable. So then you can say, well, there is something specific about that particular n that appear in the relation. And it turns out that if I choose another number, say p, much larger than n, then the corresponding periodic quotients are no more isomorphic. So it means that the value of n that may appear if I want to go in the other direction, they have to depend on my two original group gamma 1 and gamma 2. And this is where I will have more an asymptotic approach again, saying, well, if I choose gamma 1 and gamma 2, if from arbitrarily large n I have an isomorphism here, what can I say about the two original group? So that's the first obstruction to answer this question positively. Now the second one is a bit more subtle. And it goes as follows. So I will always take gamma 1 to be the free group, which generators A and B. And now this time gamma 2 will be the group with the following presentation. I have three generators, A, B, and C. And the relation will be something like C squared equals some word in A. So again, you can cook this up to make sure that gamma 2 is still a hyperbolic group. Now what's happening in this situation? Well, imagine that I choose an odd exponent, n which has the form 2k minus 1. Then, in the periodic quotient of gamma 2, if you look at this relation, I claim that this relation is just equivalent to the following one, C equals W to the AB to the K. Said differently, in an n-periodic group, if n is odd, I can always extract square roots. Every element has a square root. So that means in this quotient, this relation is useless. It's just C equals some element A and B. So it means that this periodic quotient here is just the same thing as the periodic quotient of the free group. So in this situation, I have two periodic quotients which are isomorphic, although the original group are not. And this time I cannot say, well, I can change my exponent, make it larger, or find some clever things to do. We have to deal with this kind of situation. This may happen. So to sort of go around this obstruction, I'd like to formalize it a bit. And I will say that a group G has a root splitting if write it as an amalgamated product, A and B or C, where B is the building group and C has finite index in. So typically, this kind of presentation. In addition, I would say that the splitting is non-essential if B and C are abstractly isomorphic and B is a free factor of A. So why do I add this terminology? Because, for instance, if you take the free group generated by A and B, I can already decompose it in a sort of silly way. So I say that group generated by A and B squared that I amalgamate with B over B squared. That's root splitting, but that's one that you don't want to take into consideration. So I will always look at root splitting which are essential, meaning they do not fall in this category. And the relevance of this root splitting comes from the following observation, that now if I take an exponent n which is co-prime with the index of C and B, then the periodic quotient of G is isomorphic to the periodic quotient of A. So this is exactly the same observation that we had here. Okay, so basically those are two obstructions. My exponent here has to depend on the group, and I have to be careful that some jokes may come from this root splitting. And what I'm claiming is that besides those two things, everything works as you may want. So the theorem now that we obtain is the following. So I will consider gamma 1 and gamma 2 two torsion-free hyperbolic groups. And I claim that there exists some exponent n such that the following are equivalent. Sorry, I forgot the essential assumption of torsion-free hyperbolic group without essential root splitting.
Without non-essential. Or without essential.
Essential. So the non-essential one, okay. I don't want to rule out those.
Okay.
So what's that? So where it says if, so B,
Sorry?
where it says B is a free factor of A, what should that say?
C.
So, sorry, C is a free factor of A. Yeah, thank you. C is a free factor of A, yes. So I assume that gamma 1, gamma 2, two torsion-free hyperbolic group without essential root splitting. And now I can find some large integer so that the following are equivalent. First, well, my two original group, gamma 1 and gamma 2, are isomorphic. Second, all the periodic quotients are isomorphic. And third, actually, it suffices to have one sufficiently large periodic quotient which are isomorphic to say that the original groups were isomorphic. So somehow the philosophy behind is we're trying to invert two limits. What I mean by that is that if you take an exponent n very large and you look at small balls in the K-graph of those quotients, these small balls, they look exactly like the small balls in your original group. And like say when you take n larger and larger, locally this group looks more and more alike. And you like say, well, go to the limit and your group are the same. But unfortunately it's not that easy. But that's sort of the philosophy. We're trying to invert these two limits. But the part which was really surprising to us is these three implies ones, that we don't need to know that all the periodic quotients are hyperbolic. As long as for some large n they are, the original group are isomorphic.
Yes. You say for some large n, but isn't this equivalent to ask whether it is true for infinitely many n? Because you know the.
So the statement goes as follows: you have your two input groups, and then they give you some large n.
Now, if you don't control the n, it is the same as asking it is infinitely many. I mean,
In the end, it's the same. Yeah.
No, but even not in the end. I think it's formally equivalent.
Yeah.
Yeah, but I mean, of course, that's part of the result.
No, but you
No,
don't
I mean,
need
you
an
see
even.
for one, but actually you need it for infinitely many n, for arbitrarily large, because you don't control the big n.
Well, the big n is only controlled by gamma 1, gamma 2.
Yeah.
It only depends on those. So one thing I wanted to say later, but I can say it now, is I have not thought, how to compute this one just in terms of the presentation of gamma 1, gamma 2.
But you can just check this big N, no? Until it is.
I mean, if the n is not computable from gamma 1 and gamma 2, then this is formally equivalent to saying that they're infinitely many.
Yeah, so this is a part I did not check, but that could be possible that n is computable from gamma 1 and gamma 2. This, I will not make any claim about this, but, and then if it's computable, then you know.
Yeah, of course, then you actually get the n.
Yeah.
Okay.
Other questions? Okay, so yeah, so then the next natural step once you have this is you may wonder, if you know that those two groups are isomorphic, where does the isomorphism between the original two groups come from? And that's also something that we can decide. Results I'd like to mention is the following. So this time I will assume that gamma is proportion-free, non-elementary, and pretty indecomposable this time. Half of the group without essential word splitting. So in this situation, well, every time you have a group gamma, if you take an automorphism of gamma, well, it sends an nth power to an nth power. So that will induce an automorphism on the periodic quotient. And what I claim is that, I have written that here, there exists some integer n, such that for every odd exponent larger than n, this map is always onto. So meaning any isomorphism of the periodic quotient actually comes from an isomorphism of the original group. So see, let's say differently here, if you assume that gamma 1, gamma 2 are free and decomposable, where does the isomorphism in the first item comes from? It's exactly a lift of the isomorphism between the periodic quotient. And actually, we can say even more. It turns out that this periodic quotient is co-Hopfian, meaning that every injective self-morphism of the periodic quotient is also onto. So that means also that all the injective morphisms will lift to isomorphism of the original group. And if you wonder about the converse properties, there's the Hopf property, meaning that every surjective self-morphism is one-to-one. Well, for the moment, we only know to prove this if gamma has property FA, so meaning every action on the tree has a global fixed point, or if gamma is a surface group, then the periodic quotients are off as well, for sufficiently large orders. Okay, so now I'd like to explain how this relates to the study of equations, what the starting points are our work. So the general framework as follows. So let's say I fix R unknown, x1 to xr, and I will fix a subset of the free group generating by x1 and xr, which I see as a set of equations with those unknowns, and I'd like to understand whether I can solve this equation in a periodic quotient. So, but the point of view that we adopt, that's a very classical thing, we look at the group x generated by x1, xr with relation to this set of equations, and then that's a very known fact that the solutions to R in a group gamma actually is the same thing as the morphism from G to a group gamma. And, well, the naive question, which is a bit like the one I asked about the isomorphism problem, you know, every time you have a morphism from G to gamma, you can produce a morphism from G to the periodic quotient. So a very sophisticated way to say that every solution of the group in gamma gives you a solution in gamma of gamma. And the question now is this map onto? So say differently, if you can find a solution in the periodic quotient, does it necessarily come from a solution in your original group? So imagine for a second that we know how to solve these questions. Well, how do we go back to the isomorphism problem? Well, it goes as follows. So you have two groups with their own projections on their periodic quotient. Oops, and here we have an isomorphism, so we can precompose it by this projection, and the question somehow is, can we lift it here to a morphism? So basically we try to understand the homomorphism from gamma 1 to the periodic quotient of gamma 2. So there is some little additional work that is needed to make sure that the lift is an isomorphism, etc., etc. But basically that's the idea, that if we know how to lift those morphisms, we will be able to prove some statement about also isomorphism classes of periodic groups. Okay, so the two obstructions I mentioned at the beginning, well, you can cook up several similar examples for which this map is not onto. I want to add one other obstruction that we have to take into account if we try to solve equations. So that's the following one. I will take G to be, say, a Z0 group, a finite abelian group. And say gamma is the free group with rank 2. And so now x cubed equals 1 has non-trivial solution in gamma mod gamma 3n, but not in gamma. So we also have to be careful about finite abelian group. And again, the general philosophy is that if we avoid those root splitting, if we avoid these finite abelian groups, we know how to lift this kind of model. So the statement I would like to mention is the following. So I will let G be finitely generated group, none of whose quotient and then enjoy root splitting. So that's a bit brutal assumption, but it makes the statement work nicely. And gamma will always be non-elementary quotient free. And what I claim is that, well, always the same kind of flavor. There is some exponent n, so that for every odd exponent larger than n, every morphism phi from G to gamma mod gamma n, whose image is not abelian, I have to rule out this possibility because of my previous example, lift to a morphism C tilde from G to F. So again, if you prevent those root splitting, essentially, you can lift all possible morphisms, except maybe the one with actually some torsion in the abelian image. That's on problem that may occur. So if you want example of groups will satisfy these assumptions that may look a bit stronger. You can take, for instance, a group with property effect. Because every group which admits a root splitting will have an action on the base territory corresponding to the splitting. And so if you have if every action on the tree fixes a point, none of the quotients can have a root split, for instance. So typically, if you take triangular groups or this kind of thing, these are examples of groups that satisfy this property.
So an essential root splitting can't be trivial?
Sorry?
An essential root splitting can't be trivial? Can't,
You mean that the C and the B are the same?
Yeah.
Yeah, I guess I meant all the way non-trivial root splitting. Yeah. Other questions? Okay, so, well, one other point I want to emphasize on this statement, again, that this is really an asymptotic approach. We could have fixed an exponent n, look at the quotient gamma of gamma n, and try to solve all possible equations in that particular group. So this, we don't know how to do that. So what we do, we go the other way around. We fix an equation, which is captured by the group G, and ask ourselves, can we solve the equation in periodic quotient of gamma for some n that may depend on my set of equations? And this will play a crucial role in the proof I'd like to sketch about this statement. Okay, so now let me try to sketch a bit the strategy of the proof of this theorem. And for simplicity here, I will assume that the group G is finitely presented. G is finitely presented. And so the proof goes back to contradiction. Assume that this thing does not hold. So if you write this down, it means that for every big n there is some small n, etc. So meaning you have a family of counterexamples where the exponent is larger and larger and larger and larger. So if the statement is false, it means you can find some sequence of odd integers that goes to infinity, and you can find morphism phi k from G to gamma mod gamma nk without a hidden image that do not drift. So here, if you're familiar with
Okay, no, stop it.
is it correct?
Yeah, no. I just see where you're.
So if you're familiar with techniques to solve equations in harmonic groups, that may look a bit familiar. So imagine for a second that here I don't have this periodic group, but I have a fixed harmonic group set H. one fixed group. And that my morphisms are more and more complicated, meaning that they send generators to longer and longer words. When such a thing happens, so there is a techniques developed by Rémi and Sela, where basically the morphism gives you an action of G on this fixed haplogroup H, but because it's more and more complicated, you can let it degenerate to an action on a real tree. And then you have the RIPS machinery which allow you to decompose the action in a real tree in certain pieces which are well behaved, and eventually run what's called the shortening arguments. There is a huge machinery to handle those things. So this is where the idea comes from. But now you may argue, well, first, this is not a fixed group, this group is varying, and this is absolutely not a hyperbolic group. So if you try to let these things act on the hyperbolic space, the action has to be degenerated in certain ways. So either it has a very small orbit, or it fixes points at infinity. These are the only two things you can do. So it looks very hopeless at the beginning if you try to let this kind of action degenerate. So the way to go around this is now to go back to the proof that these groups are infinite. So the key argument is the following. So to study this quotient gamma mod gamma nk, actually one possible way, well, actually all the proofs I know are more or less model of this thing. One produces a sequence of hyperbolic groups, which one can think of approximation of my parity groups. So we start with gamma, which I will say it's gamma naught k, and it maps into another one, which is gamma 1k, etc. Blah blah blah. Gamma k, okay, so that the limit of all these groups is exactly the parity quotient. So now this is where my simplification comes in picture. I have this morphism phi k from my group G to gamma mod gamma n. And because it's finitely represented, at some point all the relation of G has to be satisfied somewhere in my sequence. So it means I can lift this morphism into something which is double psi. But I cannot lift it to the very first one. So the consequence of that is this morphism has to be more and more and more complicated. As I told you, the balls in this quotient, and thus in this quotient, that looks much more like the ball in gamma when nk goes to infinity. So imagine if the length of the generator under this map phi k were uniformly bounded, at some point I could lift that to my very original group. So because my morphism does not lift, and actually also because it does not have an abelian image, if I try to choose the best lift possible, it's still very complicated, and more complicated as k goes to infinity. And the sort of miracle is that we have a uniform control on the geometry of those groups. And by uniform, I mean that this does not depend on the exponent nk, and this does not depend on the approximation I choose. So we have a uniform control. So what do I mean by control? For instance, we can let those groups act on a hyperbolic space with uniform control on the hypervelocity constant. I just said that, it's not saying much because I can always rescale my space, but at the same time I also have the control on the injectivity radius of the action, so by how much my group elements can move points. And we also have control on other parameters related to the action, asynchrocity, those kind of things. And because of this uniform control, and my morphisms are getting more and more complicated, actually we can again let this action of the group G via this hyperbolic group degenerate to an action into an R tree. So and this actually turned out to be very nice. Its arcs have torsion-free abelian stabilizers. You have some kind of stability if you know what it is. And basically, the idea that you can run the Rips Sela machinery and then decompose this as action into well-behaved pieces. So here we use Rips Sela to decompose this action. And in particular, that provides an action of G on a simplicial tree. So if you started, for instance, with a group which has property Fa, every action on the simplicial tree has a global fixed point, you already have a contradiction. If you started with a more complicated group, well, the idea is that we can in advance try to say, okay, we have a counterexample, but almost among all possible counterexamples, try the one which is as easy as possible. In a way which has to be formalized, but try to choose the easy one, the easiest one. Then we do the sleep procedure, we let it degenerate to an R tree, decompose the action on an R tree and well-behaved pieces, and then Sela provides a shortening argument which says, actually, there was an easier one. And then we get, again, a contradiction. So that's the last step of that global strategy. And so this is where we get the contradiction from. Well, I'm cheating a bit, like infusing it under the carpet, but that's the general picture in this proof. And somehow the miracle of this asymptotic approach, that imagine you only works with prime exponent. Basically, in doing so, all the torsion disappear. At the limit, you will never see something to the n equals 1. So we are working in the class of limit group that is appropriate for periodic groups. Well, the torsion vanishes. And torsion group may look frightening at first, but here, basically they're not there. We're not working really with torsion. We are really working with this approximation where the torsion is. So yeah, I think that's a good way to stop. Thank you very much.